Year 11, I'm going to be looking at the next exercise in probability, which is probability trees. Now, when we talk about probability trees, probability, the whole idea of drawing a tree diagram is the same as making a list or drawing a table. It helps you calculate all the different things that can happen. Now, the beauty of probability trees, though, is that you can do it for more than two things. So remember, if we toss two coins, you can draw a table for tossing two coins. So you can go, I can have heads, and tails, which means I can have a head and a head and a tail and a head, and a tail and a tail. But that only works when you have two things. And remember, using a table is just an easy way to make a list and making sure that you don't miss anything. So the very first question in this next exercise, and this is, I'm just going to start it like this. I'm not going to go through all the examples and stuff like that, because it's easier just if you see it via a question. So here we go. We're tossing three coins, which is why I use that example there. I can't use a table. So I start by drawing my tree diagram. So on the first coin, and remember, it makes no difference if you toss three coins or if you toss one coin three times. So the first coin can be a head or a tail. And then from each branch of those, I get another head or a tail, which confirms our fundamental counting principle, which is it multiplies, because there are two things that can happen on the first, two things on the second, so there should be four. So as you can see now, I've got four different branches. But I'm going to toss it a third time, which you should be going, that goes with the fundamental counting principle again. 2 times 2 times 2 will give me 8. And it's exactly right. I will now get 8 different things that can happen. And they're all the different things that I've got. So I can have 3 heads. I can have 2 heads and a tail, a head, a tail, and a head, a head, a tail, and a tail, a tail, a head, and a head, a tail, a head, and a tail, and a tail, a tail, and a head, and a tail, and a tail. Now remember, the tree diagram is just a way to help you count or making sure you don't miss anything. So you can now answer the 3 questions. But if you didn't need to use a tree diagram, you don't have to. For example, what's the probability of 3 tails? Well, the probability of a tail, and a tail is 1 on 8, because there are 8 things here and there's only one of those that has 3 tails. But you could have used your multiplying law, your product law. It's a tail and a tail and a tail, which is 1 on 2 times 1 on 2 times 1 on 2, which is 1 on 8. So you don't need the tree diagram if you can think about it. But sometimes you need to be able to make some other things. The next one says 2 heads and 1 tail. Well, if you just followed that and used this, you went, a head, and a tail, then you'd have to think, or I could do that this way, a head, a tail, and a head, or I could do that this way, a tail, a head, and a head, and you'd be starting to question yourself, are they all the different things that have 2 heads and a tail? Whereas if you have the tree diagram, you can quickly see 2 heads and 1 tail, 1 there, 1 there, 1 there. And yes, they are the 3 different ways you can get 2 heads and a tail. So you go, the probability of that, 2 heads and a tail, is 3 on 8. And you don't need to do the long multiplication, because here you'd have to write, all this equals 1 on 2 times 1 on 2 times 1 on 2, or, remember, or means add, n means multiply, 1 on 2 times 1 on 2 times 1 on 2, plus 1 on 2 times 1 on 2 times 1 on 2, which gives you 1 on 8 plus 1, so 3 on 8. The tree diagram simplifies that whole process. The last one here, the probability of at least one head. Well, again, if you look at the tree diagram, it makes a lot of sense because the probability of at least one head, well, there's 3 heads in there, so that's got 1 at least. That one, that's got a head, that's got a head, that's got a head, that's got a head. Oh, all right, 7 on 8. But let's say it was a harder probability and working all those things out was more difficult. Because you know that all these probabilities here must all add up to 1, whenever you have at least, you can just find the probability of this and subtract it from 1. So you could have just gone the probability of at least 1 equals 1 minus the probability of none, which equals 1 minus 1 on 8, which is 7 on 8. Now I'm using the first question to illustrate all these things because it's much easier here to draw the tree diagram and you can just see everything right in front of you there. But sometimes it's not as obvious, particularly when there are probabilities on different arms, which we're about to talk about. So we'll have a look at question 2. Now question 2, I am not going to draw a tree diagram for this. 30 cards, I'm not going to draw a branch with 30 cards and then have another 30. Like if I'm drawing 2 cards out and there are 30 and then another 30, that's 900 different branches. I'm not going to draw it. I'm just going to, and I'm going to show you a way to draw a tree diagram doing question 2a, but I'm just going to use the and or for the other ones. So what's the probability of getting 2 8s? Well, when I draw a card, I can either get an 8 or not an 8. And to help me with that, I know that, well, there's 1 card out of 30 that has an 8 on it, and there are 29 cards out of 30 that don't have an 8 on them. Now, when you're thinking about this and you're going, well, how does that work? That means rather than drawing another 29 branches, I'm just going to say that branch is worth 29. And if I follow the same procedure, I can get an 8 or not an 8. I can get an 8 or not an 8. And again, on each of these branches, because I've put the card back, 1 on 30, 29 on 30 for that one, 1 on 30, 29 on 30 for that one. It saves me writing out all 300 branches. But in the end, I'm only concerned with this branch. The probability of getting an 8 and an 8. Well, an 8 and an 8, well, that's 1 on 30 times 1 on 30, which is 1 on 900. So you don't need to draw the whole tree diagram, which is what I'm going to do for the next one. So I want to get a 3 and an 18. So I'm not going to draw the tree diagram for the next one. The probability of a 3 and an 18, I can imagine it in my head. So chance of getting a 3, 1 on 30. Then an 18, 1 on 30. Oh, 1 on 900, exactly the same. But the next question says a 3 and an 8 on either card. Well, again, I could draw the tree diagram, but I'm not going to. I'm just going to go, well, I can get a 3 and an 8 or an 8 and a 3. So that's 1 on 30 times 1 on 30, or means add, plus 1 on 30 times 1 on 30. which gives me 1 on 900 plus 1 on 900, which equals 2 on 900, or 1 on 450. Right. So that's tree diagrams. Now I want to work with question 3, and then I'm going to let you go. And I might have a go at some of the harder ones, or if you email me. So question 3. So let's create a little bit of space here. Question 3. I'm going to let's get rid of that so I can see what I'm doing. Okay, question 3. So a bag contains 5 red marbles, 8 blue marbles. This is a perfect case where I only have to draw, because all I can get is a red or a blue. So I just go, oh, I'm drawing 2 marbles out. And am I putting them back? The first ball is replaced. That's important. So I can get a red, I can get a blue. Then when I draw again, I can get a red or a blue. Or I can get a red or a blue. And that's it. There's only 4 things that can happen. I need a red and a red, a red and a blue and a red, a blue and a blue. But they have different probabilities. 5 and 8, that gives me 13. So the chance of getting a red, 5 on 13. Chance of me getting a blue, 8 on 13. Now remember, whenever you do this with probability on the arms of the probability branch, each branch should add up to 1. The 8 on 13 plus the 5 on 13 should add up to 1, which it does. So let's now have a look. Because I put the marbles back, there are 13 in there again, and the probabilities do not change. And then I just follow the arms of the branches I need. So I'm not going to do this. You can go and do it and check it out. 2 red marbles, 5 on 13 times 5 on 13, easy. A red and a blue marble, well, that's red, blue, that branch, or blue, red, that branch. And I multiply them together. 5 on 13 times 8 on 13 plus 8 on 13 times 5 on 13. Right. So now we know that. Let's go up here and see if we do some without replacement. Okay. Well, these are all manufacturers. 3 dice. Yeah, I'll come down here to 16. There are 18. Is there one where they have without replacement? I'm trying to look here. Two singers are selected. No, this is all has replacements. All right. Okay, so I'll jump to question 10. That's a nice easy one. Or one that you might find hard. 2 tennis players are said to have a probability of 2 on 5 and 3 on 4 respectively of winning. Find the probability. So 2 tennis players are said to have a probability. So we'll have tennis player 1. Now he can either win or he can lose. And tennis player 2, I said he, could be a female, they can either win or they can lose. So, what's the probability of the first tennis player? 2 on 5. 2 on 5 of winning. That means they have a 3 on 5 chance of losing. The second player, they're a bit better, or maybe they're playing a weaker opponent. 3 on 4 or 1 on 4. 3 on 4 and 1 on 4. So, find the probability that one of them will win. Now, that's a bit tricky because it says 1. It doesn't say at least. As soon as I see that, then with worded problems, you've got to be careful. That one of them will win. Does that exclude the chance that both of them will win? Well, I'm going to assume that it does. So it means that only one of them wins. So I can follow this branch, the first player winning and the second player losing, or the first player losing and the second player winning. So that gives me probability the first player wins, second player loses, or the second player loses, the first player loses, second player wins. So it's 2 on 5 times 1 on 4 plus 3 on 5 times 3 on 4. Well, that's going to be 2 on 20 plus 9 on 20, 11 on 20. And that is excluding the chance that both of them will win. What's the probability that neither of them win? Well, that's easy. That is, I'm just going to get rid of these, that and that. The probability that neither wins is that. So they both lose. Probability lose and lose. 3 on 5 times 1 on 4. 3 on 20. All right. Let's go up here when they start talking about manufacturing, and I want to do question 16, and that'll do it. Let's have a look at 13. They're making an energy drink, and they surveyed people. So they've got this relative frequency. Found that 31 people liked X drinks best, and 19 liked another brand. So they either like X or another brand. And 5 did not drink energy drinks. Okay, so this is going to be a triple. Now remember, you can do this without a tree diagram. So we're selecting 2 people. We're selecting 2 people, and see, I reckon when you select that first person, that when you select the next person, it should be out of a different probability, but they're not doing it that way. I'm looking at the answers and they're just going over the top. So yeah, we're just going to have to use a probability like it's a set theory probability, and there's not a set amount of people. So how many people are there? 13 plus 19, that's 50, plus 5 more. So that's going to be out of 55. So I'm selecting 2 people. What's the probability so I don't need the diagram, but I could draw it if you wanted. So we're selecting 2 people, and we're assuming that the probability stays the same, that there's like it's not a set closed group. One person likes X of the brand drink. So that we can have X. Now that they can only have one, and I'm going to use the notation they've got. They don't like energy drinks. Or the first person likes it and the second likes another brand. Or the first person you pick doesn't like energy drinks. Oops, I've done that the wrong way around. Doesn't like energy drinks. And the second person likes brand X. Or the first person likes another brand and the second person likes brand X. They're all the possible ways that can happen. The first person likes brand X, the second person doesn't like an energy drink. The first person likes brand X, the second person likes another brand. The first person doesn't like energy drinks, the second person likes brand X. The first person likes another brand, and the second person likes brand X. And you multiply all those out together. And so that equals, what is it? 31 like brand X, don't they? 31 like brand X, 19 and 5. So 13 on 55 times 5 on 55, all means add, plus 13 on 55 times 19. Oh, what do I mean 13? It's 31. Goodness me. 31, 19. And then we just reverse the order of these. Oh, doesn't like it. 5 on 50. It doesn't drink energy drinks. times 31 on 55, or 19 on 55 times 31 on 55. That's a terrible 5. And that equals, when I add all that up, what do we get? 1, 4, I'm just using the answers here because they've got exactly the same thing as me, 3025. Now, I actually disagree with this answer because I'm assuming that this is a closed group. So don't take this on board. I reckon this is a closed group, and that should be 5 on 54. Because once you take one of the people out, the second person, there's only 54 people because you've already taken one out. But that's not how the textbook's doing it. So ignore that. I reckon every second one in those should be out of 54. The next question, both people do not drink energy drinks. Well, and again, I reckon they're wrong. And don't like them. 5 on 55. I reckon that should be 4 on 54. They're going 5 on 55 because they're saying it's not a closed group. So it's like this is the probability of this happening, which is 1 on 121. So I want to go to this question 16, which is rolling 3 dice. Now, if I roll 3 dice, so question 16, fundamental counting principle. If I roll 3 dice, 6 times 6 times 6, there are 216 different things I can get. I'm not drawing a tree diagram with 216 different options. But I look at the questions, and the questions are all about getting a 6 or not. Well, that's much easier. I can just go, well, the probability of getting a 6 and not getting a 6, and I can do that because there are only 2 things, which means I'll get a tree diagram of 2 times 2 times 2, and that'll give me 8 things, which is much easier to draw a tree diagram for. And remember, a 6 with a dash above it means not getting a 6. Now, I don't need to write all the probability out because there's only 3 questions. What's the probability of 3 6s? Well, that's this branch. And the probability of 3 6s, a 6, a 6, and a 6, well, that's 1 on 6 times 1 on 6 times 1 on 6, which is 1 on 216. Now, two 6s. Now I have to look at it. So I'm just going to write out the sample space. That's 3 6s. That's 2 6s and not a 6. That's a 6, not a 6. 2 more 6s are getting bad, and a 6. That's a 6 and 2 not a 6s. That's not a 6, a 6 and a 6. That's not a 6, a 6 and not a 6. That's not a 6, not a 6 and a 6. And that's 3 non-6s. So the ones I need, that has 2 6s, that has 2 6s, and that has 2 6s. And it just means it makes it easier for me to count or to not mess up. So the probability of each of these, and I'm just going to write it out. So that's the probability of a 6, and not a 6. Or, so I add, the probability of a 6, not a 6, and a 6. Oops, I only wrote not a 6 there. Oh, I did write it. And the other way is not a 6, and a 6. Now, the probability of a 6, well, it's 1 in 6. The probability of a 6, well, it's 1 on 6. Probability of not a 6 is 5 on 6. And I know some of you are going to say, couldn't you just multiply that by 3? Yes, you could, because it is exactly the same thing, just in a different order, multiplied 3 times. So that's a 5. and then you pump that in your calculator. Please make sure that's the most important line, writing that, because probability is very easy to not get marks because you write a bald answer. Anyway, all of those add up, so they're all going to add up to 5 on 216, so 5, 216 plus 5 on 216 plus 5 on 216, which gives me 15 on 216. And the back of the book's telling me that that's 5 on 72. All right. 3 goes into 20. Yep, 72. Look, that should be enough for you to get through those. There's no non-replacement in any of these, which really worries me. But we'll see how you go. Good luck.